For carbon NMR, the number of peaks is equal to the number of distinct carbon environments. Number two, the greater the electronegativity around the carbon, the greater the chemical shift. So for example, a carbon bonded to an oxygen, a carbon bonded to a fluorine, or just in the vicinity of something electronegative, that drives the chemical shift up. Prime example would be the carboxylic acid group, 2 oxygens, 200 to 220. And then finally, the height of the peak is equal to sort of the number of carbons in that environment. So for example, if you have one peak which is approximately double the height of the other one, then the carbon, those two carbons may be in the same environment. So for example, it could be like two CH3 groups attached to a carbon. However, that is not always the case, but the majority of the time when you see the peak being double height to the other one being like approximately twice as much, you can think of the two carbon environments being the same. That's different to proton NMR, where the area under the peak is equal to the number of hydrogens in the environment, and that's covered in another video. So this example here, we have 2 spectra and 5 different isomers to choose from, which you can see at the bottom. What we have to do is essentially match the figure 2 spectra and figure 3 spectra to the correct molecule. So how do we go about this in the quickest, most efficient way? So let's start with the easiest one, which is rule number 1 is the number of peaks is equal to the number of environments. And also look at the types of peak present and see if they got a corresponding chemical shift matched to that functional group. So what I mean by that is, if I just take a quick look through this molecule, immediately I can see some key functional groups. So for example, the aldehyde group, the ketone group, we have alcohols, and we have this one, which is kind of forgotten about at A level and advanced placement chemistry, and that's called the ether functional group. The ether functional group is an oxygen which is sandwiched between 2 carbons either side. And of course, your alkene double bond. Right, so the first one I'm going to look for is the aldehyde, because that is such a distinct peak on a carbon graph and has a really high chemical shift. If you look at the data table that I've attached below, we can see that the aldehyde carbon has a shift around about 190 to 220. And if you look at both spectra, there isn't a peak in the 200 range on either one. So immediately I can rule out this as being a correct answer. So that's gone. Right, the next thing to look for is the ketone group. So the ketone group is, again, up within the aldehyde range, 190 to 220, and it's just not present. So that's gone as well. So already we're down to the alkene and ether and the alcohol. Right, alkene. That's a distinct one. So the alkene double bond has a chemical shift of starts at around about 120, I would say, or 110 up to 140. So do we have anything between 110 to 140? Well, not in this one, but we certainly do on that one. So that is indicative of a carbon-carbon double bond. And the reason why there are 2 peaks present in that alkene region is one peak will belong to one carbon, let's call it A, and then the other one will belong to carbon B. The only molecule that has a double bond is this one here. So therefore, figure 2 must be molecule R. So this one belongs to R. Which peak is carbon A and which is B? So if I call this one A and this one B, we can see carbon B is attached directly to a long alkyl chain with an OH on the end, and then carbon A is just attached to a CH3. The greater the electronegativity of the chain, the slightly bigger the chemical shift. So we could probably say that this is going to be B and this one belongs to A. Okay, so now we got figure 3. Let's consider what is those set of peaks. So looking at the data table, they all start, you can see they start at about 20 and finish at around 35. Carbon-carbon bonds that fall within that range are just this straightforward CC bonds. We can rule out CCl, CBr, but then we have this set of peaks here, which is between, say, 68 to 72. If you look, the only bond that matches those peaks in the data table is the CO bond. So that could be the CO bond of an alcohol, or the CO bond of an ether. So how do I know which one it's going to be? Well, I need a bit more information. So if we look at this molecule, so let's just draw part of it, and we've got this bit there, right? So that would be a CO bond, and that would give rise to one peak. However, in the spectra, we can clearly see there are two peaks in this region. So that suggests, just like with the alkene, there must be the presence of two CO bonds. Otherwise, there wouldn't be two peaks. So two different unique CO bonds. And if we look at carbon, if we look at the molecule T, we can see there is actually two different CO bonds. So if I just use a color to highlight this, so there's this one where that carbon in green is attached to the oxygen there. And then the one immediately next to it, if I just put this one in yellow, is that one there. So why are they different? Because the green one is a CO bond, which is attached to a CH2 there, whereas the, just put them in green. So that CO bond is directly attached to a CH2 group, whereas the other carbon in yellow is attached to a CH3 group. So chemically, it's not the same environment. They're not identical. And because they're not identical, that means you're going to have a different peak for each one. So that means T must be that one there. So to summarize, figure 3 is T and figure 2 is R. Okay, finally to finish, let's go through the thought process. So what did I do? I looked at the options available to me, and in the first instance, I looked for functional groups in the molecules that did not have peaks in the spectra. So for example, there was no aldehyde, there was no ketone. Get rid of the molecules that it cannot be. Then secondly, just dive down into the functional groups that are present and see where those peaks should be. So for example, the alkene, that was a dead giveaway, between 140 and 120. So that's how I knew molecule R was going to be an alkene.